So a bit more about the chain rule for multivariable functions. So previously I talked about um, one or two steps that you could do in order to get what the chain rule is. But that was coming from the point of view of I knew what the chain rule was, and all I had to do was sort of show you one or two steps. Now let's take it from a different point of view. Suppose you did not know what the formula for the chain rule was. How would you get it? So here's an outline of how to first guess what the formula might be and then also how to prove it using the idea of linear approximation. So here's the question. Suppose z equals f of xy and x equals x of t and y equals y of t. What is df dt? And again, suppose we are starting just from scratch. We don't know anything. So here's what we do. So for our differentiable function f, and we're going to be at the point xy equals a comma b. So let's say that we know what the value of the function is at that point, f of ab equals c, and we know the value of the derivative, the partial derivatives at that point. So f sub x at ab equals r, and f sub y at ab equals s. So now we can write down the linear approximation for our function. So at our point, linear approximation is r for f is r times x minus a plus s times y minus b plus c. As long as we put the plus c in front, doesn't matter. Okay. So next we've also got the functions. X of t and y of t. So once again, let's suppose that we know the value and the derivative for each of these things. So, and we could pick any value we could say any value of t gets us to our point, x equals a, y equals b. I'm just going to use t equals 0. So at t equals 0, the x of 0, the x value is going to be a, and then the y of 0, y value is going to be b. And let's say that we also know our derivatives. So dx dt equals m, and dy dt equals n. Okay, so now let's write the linear approximations for that. So we can say that x of t is approximately mt plus a, and then y of t has a linear approximation nt plus b. Okay, so now I've got at our point xy equals ab, and we're saying t equals 0 in our expression. We've got linear approximations for everything. Okay, so some other facts on the side, just to recap what we just said. And now let's get into it. So now let's plug that in, and we can write the linear approximation for f in terms of t, and that's the bottom line there. So at our point xy equals ab, then we have that f equals r times, instead of, oops, sorry, that's the wrong line. That's old business. Okay, so now let's rewrite f as a function of t. So f of xy equals f of xt comma y of t, and what does that wind up being? So it's approximated by r times, and it was x minus a, so now it's mt plus a minus a, plus s times, it was y minus b, so that's now nt plus b minus b, and then plus c. So simplify that, and that simplifies quite a lot. So the linear approximation for f in terms of t is rmt plus snt plus c. And now we can do a calculation for df dt, and once again, it's all approximation. So df dt is approximately rm plus sn. Okay. Now remember, I used the letters r and m and s and n to represent derivatives. Let's go back and plug in what those derivatives were. So r was just df dx at the point AB, and m was just dx dt at this particular point. And then s was df dy at my particular point, and then n was dy dt at this particular point. So here's what we know. We know that df dt is approximately that expression right there. But check it out. This approximation only involves first derivatives. So for df dt at the point AB, there's actually an equation. So df dt at the point AB equals blah, blah, blah. But notice that the point AB could just be any point. And as a result, we now have the chain rule formula. So this method was really interesting, and it's something that we're going to use in the future, which is where we began by saying we don't know what the rule is. Let's try to guess the rule. How are we going to guess the rule? By taking linear approximations of every function or expression we're dealing with, and then just plugging it in and seeing what we get. And just by seeing what we get this last line, which is we get the chain rule.